Okay. Today we're going to talk about got some stuff opening up here. Applications of logarithms. These are some practical applications of why you might need logarithms at some point. The first one is very practical because at some point I hope you are investing your money and making some decisions about that. So we've already used this compound interest formula before, and example number one is very much like what we've done in the past. And so I want to go over that with you on how to use these compound interest formulas. And we're going to go through and talk about how to set them up. And basically the thing you need to do when you're working with any kind of a word problem is identify what you know, what you're given. This is really going to be important when you get down into, well, anything, math, but especially when you get in physics, to identify what you know, what you're given in the problem, and what you're looking for. So the first thing we're going to do is write down all the variables that we're given. We're given amount, the principal, we need to know the rate, the number of compounds in a year, and the time. And the time has to be in years in these. Okay, so we're going to look at the problem and see what we are given. Courtney wants to have $5,000 in an account after 12 years. That's what she ends up after the investment time, so that's A. Time then was given to us was 12 years. Time will be in years. Earns 7% interest. Remember, that's your R, and when we do the interest, we change it from a percent to a decimal by dividing by 100 or moving the decimal place to the left 2 places. Compounded quarterly, that means interest is calculated 4 times a year, so that's n equals 4. And how much will she need to invest initially? So this is what we're looking for right here. Or you could just put a blank and it's dollars. Okay, so that's what we're looking for. Putting it in the formula, you've got 5,000 is equal to P 1 plus 0.07 over 4 to the 4 times 12 or 48. Okay. Now you can just put this in your calculator. We're going to have to solve for P, so we're going to divide 5,000 by all of this, the 1 plus 0.07 over 4 to the 48th power. And when you do that, you're going to get about 2,174 and 29 cents. And remember that when this is dollars and cents, you need to carry it to a couple decimal places. This is a 7. Couple decimal places since it is dollars and cents, and that's your answer. Now in number 2 and 3, you're going to have to use logarithms because the question in this is how long must she leave the money, which is T, and again, how long will it be before his investment is grown? So if you notice, the T right here is up in the exponent, and the way to solve when your variable is in the exponent many times is to use logarithms. So let's write what we are given, or what the variables of the equation are, and fill in what's what. Suppose Heather has 2,000 to invest. The amount you invest is your principal. So that's 2,000. Earns 10% interest, so 0.1 is your 10% interest. Semi-annually means it's twice a year, so the number of compounds is 2. And she wants to know how long she has to leave it in order to end up with $5,000 at that interest and that number of compounds. And that may be something I ask on a test. I might give you 2 different scenarios and say which is the best investment. You know, so many compounds, so much interest. And it may not be obvious necessarily, so I'll ask you to figure that out. So let's set this up. 5,000 is equal to 2,000. times 1 plus 0.1 over 2 to the 2t. Okay. 5,000 divided by 2,000. When you do that, your zeros are going to cancel. 5 halves is 2.5. 1 plus 0.1 over 2 is 0.05, so that's going to be 1.05 to the 2t power. Okay. Now we're going to take the log of both sides. This is that example A that we did in 2.5 where we don't have any logs. So you're going to say the log of 2.5 is equal to 2t times 1.05. Oops, excuse me, the log. I'm an eraser here. There it is. Okay, log of 1.05. Divide by 2. We want the t by itself, so we're going to divide by 2 log 1.05 on both sides. Now the problem with doing that, is you have to remember, put your denominator all in parentheses, the whole business. And this log 1.05 from the calculator will be in parentheses. So you'll have to close your parentheses twice at the end of after the 1.05. So then we end up with t, when you do the calculation, t is equal to 12.99, no, excuse me, 9.39. Slow down a little so my writing is somewhat legible. 9.390 if you want to make it years. So about 9.5 years for that money to grow from $2,000 to $5,000 at 10% interest compounded twice a year. All right, next one, same thing. List what you know. A, P, R, N, T. Scott invests $5,000, so that's his principal. At 8%, compounded quarterly, so you're 4 compounds. T is what we're looking for, and wants to end up with $14,000. Okay, so we have 14,000 is equal to 5,000. 1 plus 0.08 over 4 to the 4t power. 14 fifths, because the thousands will cancel, is 2.8 equals, all that adds to be 1.02 to the 4t. Log of both sides, so we have log of 2.8 is equal to 4t log 1.02. Divide by 4 times log 0.02. So we end up with log of 2.8 divided by 4 times the log of 1.02, and that's going to equal t. And when we do the calculation, that's 12.999, or about 13 years. Okay, be sure you can get these numbers in the calculator, because I don't like to think that you will end up with a calculator causing you to make a mistake on the test just because you haven't practiced entering these things in a calculator. All right, let's move down. The next set of problems are radioactive decay problems. So let's go up to this one. And I need to come over here just a minute. Okay. And we need to change to the pen. All right, here's the basic formula for radioactive decay. It takes for a half-life. And what half-life is that over every radioactive element is out of balance in the nucleus. And it will, not all isotopes are radioactive, but it causes the nucleus to emit particles or rays at a very regular interval. And after that interval has gone by, half of it has converted to either a more stable isotope or sometimes even to a different element altogether. So the half-life, for example, of sulfur is 87.1 days. You start with a 2-gram sample. After 87.1 days, you're going to have 1 gram of sulfur 35, and the other will have changed to something else. So half of it goes away and changes at each of those intervals. And so since that, they can date materials with radioactive substances and do other things with radioactive substances. So this is why this is half. And this formula always stays the same. So again, we're going to list what we are given in the problem. We have N. N sub 0 is our original amount we start with. Time and half-life. Okay. The half-life of sulfur is 87.1 days, so that's that. How much of a 2-gram sample, so we started with 2 grams. We're looking for this, how much remains after 100 days. Well, 100 days is a little over the half-life, so it should be something less than a gram if we just logically try to figure out if our solution will be reasonable. So we'll put that in our formula. And we'll go here to, and I'm not going to write the answers down for these, but we can put them in here anyway. The half-life of sulfur is 87, so we're going to put it in the formula. N is what we're looking for. 2 to the 1/2, 2 times 1/2 raised to the 100 over 87.1 days. And then you just do this calculation. And when you do the calculation, it should come out about to 0.9 something, something, something. I don't have my calculator here in front of me, and so I'm limited on what I can get done in that regard. That's going to come out to be 0.9024. I went ahead and put it in the calculator. For the next two, you're going to list what you know, what you don't know. And where this time, we're going to have to use logarithms. One isotope has a half-life of 23 hours, isotope of chromium. So it's 23 hours. Okay. How long does it take 50 grams to decay to 40 grams? So we start with 50, and we decay to 40, and we're looking for the time. Okay. So we go through here, and we have 40, setting it up, is equal to 50 times 1/2, or 0.5 if you want to use 0.5, to the T over 23. 4/5 is 0.8. So 0.8 is equal to, I'm going to go ahead and put 0.5 times T, or raised to the T over 23rd power. Log of both sides, log of 0.8 is equal to T over 23 times the log of 0.5. Now to solve this, you divide the log of 0.8. You're going to end up with 23 times, so because to make, we always do the opposite, this is divided on this side, so we're going to multiply over here. So we have 23 times the log of 0.8 divided by the log of 0.5 is going to give me t, and that should be about 7.404, and the unit needs to be the same as this, so it will be hours. My pen must be losing charge. It's jumping around. 7.4 hours. All right, so let's kind of hurry through this next example since I seem to be having a pen issue. Okay. 25 kilograms of a 100 kilogram sample. So we must have started with 100. We ended up with 25. Carbon 14 remains after 12,000 years. So what is the half-life? So this is what we're looking for. Setting it up, we have 25 is equal to 100 times 0.5 raised to the 12,000 over h. All right, so when I divide 25 by 100, I have 0.25 is equal to 0.5 raised to the 12,000 over h. Take the log of both sides. Okay. Now I need to solve for h. So this is going to end up being h is equal to 12,000 times the log of 0.5 over the log of 0.25. When I undo that and figure out that, so and that comes out to be 6,000 years. Which you could almost logic through that one because half of a half is a quarter. So half of it was gone in 6,000 years, and another half, down to 0.25, was at another 6,000 years. Okay, so that's how you do half-life and compound interest. And that's about all the application type problems we're going to have. There are others. There's some population growth and various things, but that's all we're going to work with today. So, thanks for your time.